Welcome to Science for Sleep, where wonder and calm meet. Each night we drift through galaxies, oceans, and mysteries of the natural world, not to startle, but to soothe. So, take a deep breath. Let curiosity slow your thoughts, and fall asleep to the sound of discovery.
When 3I, Atlas, met the Sun, what science discovered from its visit? The galaxy that makes wanderers. Imagine yourself floating above the quiet surface of Earth. The sky around you is dark and peaceful, and the world below turns slowly under a soft blanket of clouds and drifting lights. From this calm place, you begin to rise. The world becomes small, and the glow of the atmosphere fades into the blackness of space. Stars appear like distant lanterns, scattered across an endless night. With every moment you drift farther from the noise of human life and closer to the deep stillness of the cosmos. Your breath slows and your body relaxes as you let yourself be carried through the silence. This is the beginning of our long, gentle journey, a journey that leads toward the origins of a traveler called 3I Atlas. To understand what the Sun eventually did to this ancient object, we first need to understand the galaxy that shaped it. The Milky Way stretches around you like a river of pale light. It is large and quiet and beautiful, and it spins slowly through the universe. Our Sun is only one star among hundreds of billions, and from a distance, it no longer feels dominant. It becomes a small, bright point surrounded by other stars that shine with equal calmness. As you float farther outward, you can sense the structure of the galaxy in a new way. The Milky Way is a spiral system with long arms that curve gently outward from a dense central bar. It is about 100,000 light years across, and it rotates once every 230 million years. The spiral arms are the busy regions where new stars are born from clouds of gas and dust. Farther out lies the thick disk, and beyond that a vast halo of ancient stars and dark matter. Our Sun lives in a quiet part of one of the smaller spiral arms. It is called the Orion Spur. This location protects our system from violent gravitational disturbances and allows Earth to exist in calm stability. But not every object in the galaxy enjoys such peaceful stability. Some are thrown out of their birthplaces and forced into a drifting life. These are the wanderers. These are the interstellar objects. To understand 3I Atlas, we must travel back to the early life of distant star systems. Imagine a young star forming from a collapsing cloud. Around it forms a spinning disk of gas and ice, where planets and comets slowly take shape. Small grains of ice collide and stick and grow into larger clumps. Over thousands of years, these clumps become kilometer-wide bodies, which we call comets. They orbit their stars in wide, cold paths. But a young planetary system is chaotic. Large planets like Jupiter or Neptune can form and disturb the orbits of smaller icy bodies. A single close encounter can fling a comet outward so fast that it escapes the gravity of its star forever. It becomes unbound. It becomes an interstellar traveler. It begins a journey not meant to return. This is most likely how 3I Atlas began its existence. Long ago, around another star, it formed in the cold, quiet region far from the warmth of its sun. Then, through the slow push and pull of gravity, it was cast out. It drifted away into the darkness. Once an object enters interstellar space, it enters a great silence. Temperatures fall to nearly absolute zero. All motion slows. Ices lock into hardness. There is no sunlight and no day or night. Only a perfect stillness that lasts for millions or even billions of years. 3I Atlas likely spent most of its life in this deep cold. It did not change. It did not warm or glow. It simply traveled. A lonely fragment of another planetary system moving through the wide gulf between stars. Imagine this silent traveler moving through the galaxy. No engines, no direction, no purpose beyond drifting. Around it, the galaxy turns slowly. Stars pass at great distances. Clouds of gas scatter faint light. Nothing touches it. Nothing wakes it. The object remains frozen in a kind of cosmic sleep. This long journey continued for so long that the original star that birthed it may no longer exist in the same way. It may have aged or moved far across the galaxy. The path of 3I Atlas carries no memory of its home. Only the icy chemistry deep inside it remembers the conditions of its birth. Then, at some distant point in time, the gravity of our sun reached out across space and tugged on the tiny nucleus. The pull was small, but steady. Over years and decades, the path of the ancient comet bent ever so slightly toward our system. The sun invited the wanderer inward. It was the first time in untold ages that it approached a source of warmth. As it drew closer, the faintest hint of sunlight touched its frozen surface. At first, nothing changed. The object remained asleep. But as it came within the outer boundary of the solar system, the sunlight grew stronger. At a distance far beyond the orbit of Mars, something remarkable happened. 3I Atlas began to wake. This awakening was detected from Earth. Telescopes saw a thin haze forming around the nucleus. The comet was becoming active earlier than most comets do. This is because its ices were not dominated by water. Instead, they were rich in very volatile substances like carbon dioxide and carbon monoxide, which can sublimate long before water ice warms enough to melt. This early activity told astronomers that 3I Atlas was different from most comets born around our Sunday. It carried a chemistry shaped by a much colder region. Its ices held clues about its original star system. The sun was warming it now and causing a gentle release of gas. A soft coma formed around the nucleus, and a faint tail began to stretch away from the Sunday. The wanderer was slowly coming alive after billions of years in the dark. You may imagine it like a traveler stirring from a long sleep. The surface warms. Frozen gases rise from the crust. Dust grains lift into space. Little by little, the object brightens and reveals itself. The sun has not yet touched it deeply, but the process has begun. The meeting between our star and this ancient visitor is approaching. This first chapter is only the gentle introduction. The sun has begun to whisper across the cold surface of the comet. Soon it will speak more loudly. Soon its heat will reach deeper. Soon the secrets locked inside the nucleus will be released in a slow unfolding of chemical light. For now, the comet continues its quiet inward drift. The planets circle calmly. The sun shines with steady warmth. And the ancient wanderer moves toward a moment it has not experienced since the beginning of its existence. The long journey from interstellar space is almost over. The meeting with our sun is beginning. In the next chapter, we will follow the moment when humans first discovered 3I Atlas and recognized it as the third interstellar visitor ever detected. But for now, let your breath deepen once more. Feel the calm of a galaxy that creates wanderers and patiently waits for them to return to the light. The discovery of 3I Atlas. Imagine the slow, early morning quiet on Earth when most people are still asleep and the sky above the mountains of Chile is clear and dark. Telescopes rest under the cold air, waiting for the first stars to appear. Far from the noise of cities, far from any distraction, astronomers run patient instruments that scan the sky every night. These systems search for asteroids, comets, and any moving object that might drift across the steady glow of the stars. Among these is an automated sky survey called ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System. It was designed to look for objects that might threaten Earth, but it also finds things that simply drift through space unnoticed by human eyes. In the calm, early hours of July 1st, 2025, the ATLAS survey in Chile detected a faint moving point of light. It was so dim that at first it appeared no different from thousands of other minor objects that crossed the sky each night. The software simply marked it as something worth tracking and placed it in the long queue of newly seen objects. But within hours, astronomers began to notice something unusual. The motion of this small point did not match the typical path of an asteroid or a long-period comet returning from the outer reaches of our own solar system. Instead, the object appeared to be traveling on a path that did not curve back toward the Sunday. It was gliding inward on a trajectory that suggested something rare, something unbound. When an object is gravitationally tied to the sun, its path forms a closed shape, like an ellipse or a circle. Even long-period comets, which take thousands or millions of years to return, are still bound by the sun's pull. But on that quiet morning, the new object showed the very first hints of a different kind of orbit. Over the next 24 hours, astronomers began to fit the data more precisely. The uncertainty slowly reduced, and the orbit began to take shape. What emerged was a hyperbola, the signature of an interstellar visitor. It is important to pause here and imagine what this means. A hyperbolic orbit is not a loop. It is a single sweep past the Sunday. The object approaches once, then leaves forever, never returning, never slowing, never circling back. Only 2 objects had ever been confirmed to follow such paths. The first was 1I Oumuamua, discovered in 2017. The second was 2I Borisov in 2019. To find a third is a sign that interstellar wanderers may be far more common than once believed. As the hours passed, astronomers dug through older images to see if the object had been captured earlier. This process is called precovery, because it recovers images taken before the official discovery date. Soon they found faint traces in data from late May and from different telescopes, including wide field surveys that cover the sky each night. These earlier images confirmed the path. The object was not bound to the Sunday. It was entering our system from interstellar space, and it would leave it again after a brief encounter. This object received its official name, C/2025 N1 Atlas. And when the orbit was fully confirmed, it received another designation, 3I, the third interstellar object ever found. Yet something else stood out in those early images. The object was already surrounded by a soft haze. It was active. It was producing gas and dust. This meant it was a comet, not an asteroid. This also meant it carried volatile ices that were sublimating even at large distances from the Sunday. Most comets from our system stay quiet until they reach about 3 astronomical units from the sun, or closer, because water ice does not sublimate much in the cold outer regions. But 3I Atlas showed signs of outgassing at roughly 6 astronomical units, which is beyond the orbit of Jupiter. The only way an object can wake this early is if it contains very volatile ices, such as carbon dioxide or carbon monoxide, which sublimate at far lower temperatures than water ice. This is one of the first clues that told astronomers the object had a very different chemical makeup than typical solar system comets. A comet formed under another star carries the imprint of that star system's conditions. Many planetary systems form in colder regions or produce comets with different ratios of gases and dust. 3I Atlas was now revealing its nature long before reaching the warmth of the inner solar system. The sun was beginning to warm it from an enormous distance, and even this faint touch was enough to awaken the long frozen surface. Meanwhile, back on Earth, the discovery spread silently through the scientific community. It was the type of news that moves fast between observatories and researchers, but is not yet known to the wider public. The excitement, however, grew rapidly. Telescopes began scheduling observations. Large facilities like the Very Large Telescope, the James Webb Space Telescope, and radio observatories started making room in their schedules. Even the Hubble Space Telescope prepared to capture images despite its busy workload. Everyone wanted to study this object because a visitor from another star system carries information that cannot be found anywhere else. Imagine the astronomers watching the data come in. A faint comet, a glowing coma, a thin tail, all at a distance where sunlight barely warms its icy surface. It is as if the comet is whispering a story before it even reaches the Sunday. Every night, the orbit became clearer. The path was hyperbolic, with an eccentricity slightly above 1, meaning its speed was greater than the amount needed to escape the sun's gravity. There would be no second chance to study it. If humans wanted to understand this object, the time was now. As the days passed, the comet brightened gently, though never enough to be seen with the naked eye. Its distance from Earth remained large, and it would never pass close. This is important to remember, because while interstellar comets create curiosity, they do not threaten Earth simply by passing through the solar system. 3I Atlas never came closer than about 1.8 astronomical units, which is farther than the distance between Earth and Mars. Its orbit was safe, quiet, and predictable. What made it extraordinary was not its brightness or danger, but its origin. An object older than our sun was approaching from deep space, carrying a chemical fingerprint from another stellar nursery. Observations showed that the coma of 3I Atlas contained strong traces of carbon dioxide gas, and that the ratio of carbon dioxide to water vapor was extremely high. Later measurements revealed a ratio of about 8:1, one of the highest ever seen in any comet. This suggested that the object formed in a colder region than typical comets in our own system. As researchers continued to measure the composition, they also detected unusual signatures of nickel gas and only faint traces of iron. This imbalance created curiosity, because on most comets, iron and nickel appear together in similar proportions. Something in the history of 3I Atlas had altered these ratios. Some believed this was due to cosmic rays in deep space, slowly altering the minerals in the nucleus. Others suggested that the comet's formation region had unique chemical gradients. The truth is still unknown, but the data is real, and it adds to the mystery of this silent traveler. During the discovery phase, astronomers also tracked the comet as it approached its closest distance to Mars. The planet's orbit placed it in a good observing position, and missions such as Mars Express and the Trace Gas Orbiter plan to make measurements. These moments become valuable because views from another planet allow different angles of observation and reduce the limitations caused by the Sun-Earth alignment. All of this activity happened before the comet even reached the inner solar system. This early period was filled with anticipation. The sun had not yet fully revealed its influence on the comet, but the object was already telling us about the place it came from. Every new observation was a gentle unfolding of ancient information carried across interstellar space. It felt as if the cosmos had delivered a small, icy message to our doorstep, and the world's astronomers were gathering in quiet excitement to read it. Now imagine yourself drifting beside this comet, still distant, still faint, still awakening. The sun glows ahead of it like a warm lantern in the dark. The planets spin calmly in their orbits. Telescopes on Earth and in space follow its path with patient curiosity. The story of 3I Atlas has just begun. The discovery is complete. The identity is confirmed. The interstellar traveler is now on record as the third known visitor from another star system. In the next chapter, we will watch the sun begin to shape this object more strongly. We will witness the comet grow brighter and more active as it approaches perihelion. We will see what sunlight does to the outer layers of an ancient nucleus that has slept for billions of years. For now, take another slow breath and feel the calm of discovery. A faint point of light has entered our world, and the universe has quietly opened another page for anyone willing to listen. The path toward the sun. Imagine the slow unfolding of days as 3I Atlas continues its quiet journey inward. The comet drifts through space as gently as a feather falling through still air. There is no rush and no urgency in its movement. Every moment is unhurried. Every change takes place over weeks and months, and the universe gives it all the time it needs. Far behind it lies the emptiness of interstellar space. Ahead of it glows the steady warmth of our Sunday. Between those two realms, the ancient comet moves in calm silence. As the comet approaches the region where the gravitational pull of the sun grows stronger, its speed begins to increase. This happens slowly at first, and then more noticeably as it crosses the outer boundaries of the solar system. Even here, the sunlight is faint. At these distances, the sun appears no brighter than a strong star. Yet for a body that has slept in darkness for billions of years, even this faint touch of light begins to stir subtle changes in its icy surface. The nucleus of 3I Atlas is small and dark. It is made of dust and frozen gases fused together in a fragile structure. As the sunlight warms its surface, the most volatile ices begin to sublimate. Carbon dioxide and carbon monoxide emerge first, because they require very little heat to transform from solid to gas. This low-temperature awakening is what astronomers first noticed, and it told them immediately that this comet was fundamentally different from typical comets in our own solar system. The early activity allowed them to track the shape and growth of the coma as the comet moved closer to the Sunday. Day by day, the coma expanded. It formed a gentle, glowing cloud around the nucleus and created a halo that widened as more gas streamed away. Dust particles lifted slowly from the surface, creating a diffuse tail that stretched outward into the solar wind. This tail was still faint, barely visible, even through powerful telescopes, but it marked the beginning of the comet's response to the Sunday. It was the first sign of what sunlight was capable of doing to an object that had been frozen for ages. As observers watched the comet from Earth and from space-based telescopes, they noticed something else. The tail was not symmetrical. It faced away from the sun as expected, but there was also a gentle jet-like feature pointing slightly sunward. This indicated that some parts of the nucleus were warming unevenly, and that sublimation was happening more intensely on certain patches of its surface. The sun was beginning to reveal the structure and rotation of the comet through these delicate plumes of gas. The path of 3I Atlas brought it inward toward the orbit of Mars. The geometry between the comet, the Earth, and the Sun created periods where Earth-based observations became more difficult due to the angle of sunlight. During these times, telescopes had to wait for better viewing conditions or rely on spacecraft positioned elsewhere in the solar system. Mars became a useful vantage point. Spacecraft orbiting Mars planned to use their instruments to observe the comet as it passed near the Martian distance from the Sunday. These multi-angle observations would help refine models of its coma expansion and tail structure. Meanwhile, astronomers continued to refine the trajectory of the comet. Every new observation helped reduce the uncertainty in its orbit. The path became clearer, and the timing of its closest approach to the Sun, known as perihelion, became more precise. The comet would not come close to Earth, and it posed no threat. Its path was set, and it would sweep past the Sun at a distance of a little more than 1 astronomical unit. This distance placed it between the orbits of Earth and Mars, though on a different plane and angle. The trajectory was steep and fast. The comet would come in and then depart, never bound and never returning. As the comet moved inward, its brightness increased slowly but consistently. The coma grew larger. The gas production increased. Each change was recorded in calm detail by observatories around the world. The James Webb Space Telescope prepared spectroscopic measurements that would reveal the exact chemical composition of the gases escaping from the nucleus. These data would confirm the extremely high carbon dioxide content that was already suspected from earlier observations. Other telescopes in Chile and Hawaii looked for dust grain sizes in the tail and found evidence that the comet was releasing fine particles that scattered sunlight in delicate patterns. The presence of nickel gas around the comet became a focus of intense study. Nickel has a higher sublimation temperature than some other elements, yet it was present even in the early stages of activity. This meant that the surface or near-surface environment of the comet contained nickel in a form that could be released under relatively gentle heating. Some scientists proposed that cosmic rays had altered the minerals in the nucleus during its long journey through interstellar space, creating nickel-rich compounds that broke down under sunlight. Others suggested that the comet's birthplace might have had unique chemical characteristics that favored nickel-containing materials. Whatever the reason, the sun was now drawing these materials outward, revealing them to human instruments for the first time. During this stage of the approach, the comet became a subject of steady global observation. The steady hum of scientific work continued around it. Every night, data flowed through cables and servers. Every morning, astronomers examined new spectra, new brightness curves, new images. The comet itself remained silent, drifting forward without any awareness of the attention it received. It simply followed the path carved by gravity long before humans existed. Imagine yourself drifting alongside it at this moment. The sun looks brighter than before, and its warmth feels gentle but constant. The coma around the nucleus glows softly like a faint mist. Dust particles swirl slowly through the thin gas, forming a pale veil that stretches behind the comet. Ahead, the sun grows larger. The path becomes steeper as the comet begins to fall deeper into the solar gravitational well. There is no sound in this journey, no sensation of speed, only a smooth, continuous movement that feels like floating through a dream. As it crosses the orbital distance of Mars, the comet enters a region with stronger sunlight. This is the point where ordinary comets fully awaken, and 3I Atlas is no exception. Its activity increases noticeably. The coma expands more quickly. The tail lengthens. Spectra reveal that water vapor now joins the gases released from the surface. This marks the moment when the sun is warm enough to reach the deeper layers of the nucleus and release the more stable ices. The comet brightens as these new gases escape, and the structure of the tail becomes more complex. The sun begins to influence the comet more strongly with each passing day. Solar radiation pushes dust particles outward. The solar wind shapes the ion tail, creating a long, thin stream of charged particles glowing faintly blue when captured in long exposure images. The comet responds to all of this with slow physical changes. The shape of the coma becomes more defined. The nucleus rotates, and different regions face the sun in sequence, revealing new outgassing jets. Each jet carries ancient chemical signatures from the interior of the comet. These materials have not seen sunlight since the object was first formed around another star billions of years ago. As the comet approaches closer, astronomers prepare for the moment when the sun's light will reveal the deepest truths about the wanderer. Every comet is unique, but an interstellar comet is a message from another world. It carries within it the temperature, the chemistry, and the dust conditions of its birthplace. The sun, by warming it, gives humans the chance to read that message. The approach phase is the slow opening of a long-sealed cosmic letter. Every plume of gas, every dust, grain, every spectral signature is a line of ancient information rising into space for the first time. During this time, the public begins to hear more about the comet. News spreads softly through articles and brief reports. People learn that another interstellar visitor is passing through our solar system. Yet unlike Oumuamua, which was mysterious, and unlike Borisov, which was clear and bright, this visitor is subtle. It is faint. It does not approach Earth. It does not create dramatic skies. Instead, it brings quiet knowledge. It brings chemical signatures that cannot be found in any other object. It brings a story that must be told through scientific instruments rather than human eyes. The sun now dominates the next stage of the journey. The comet will draw closer still, and its activity will rise even more rapidly. In the next chapter, we will watch as the sun touches the comet in full strength, heating it, shaping it, and revealing the complex interior structure that has been hidden for billions of years. For now, breathe gently, and imagine the slow fall of the comet as it moves through the quiet dark toward the light ahead. The meeting between the sun and the ancient wanderer is approaching, and the story continues with growing calmness and wonder. When the sun begins to shape the wanderer, imagine the sunlight growing slowly stronger as 3I Atlas continues its quiet descent toward the inner regions of the solar system. The comet has traveled across 1 billion years of darkness, and now every hour brings it closer to a star that has the power to reshape its entire structure. Nothing in its long journey through interstellar space has prepared it for this level of warmth. The sun is no longer a distant glow, but a bright golden sphere that fills more of the sky with each passing day. The ancient nucleus rotates gently, and the sunlight reaches its surface in long, sweeping arcs, touching regions that have not seen light since the beginning of its existence. As this light falls upon the surface, the comet responds with slow changes. Layers of ice within the nucleus begin to warm and release gas that has been trapped deep inside. This gas rises through cracks and pores and escapes into space, carrying with it grains of dust and fragments of ancient material. The coma becomes denser and wider, forming a glowing envelope around the dark nucleus. Under the sunlight, this envelope grows into a soft, luminous cloud. It appears smooth from a distance, but within it, countless tiny particles drift in gentle spiraling motions, shaped by the push of the solar radiation. Day by day, the sun warms deeper into the nucleus. The outer layers, which contain the most volatile ices, sublimate first. Carbon dioxide and carbon monoxide escape easily. Beneath them lie layers of water ice, mixed with dust and organic compounds. As the sunlight reaches these regions, the water begins to sublimate as well. This stage causes a noticeable rise in the comet's activity. Jets of gas burst from the surface more often, and the tail becomes longer and clearer. These jets behave like small rotating fountains that turn as the nucleus spins, revealing the rotation period and the structure of the surface. The sun continues to shape the comet as it moves inward. When the sunlight strikes one side of the nucleus, that region becomes active, while the side in shadow remains quiet. This creates patterns in the tail that astronomers on Earth can detect. Some regions of the nucleus may contain denser patches of dust, while others contain purer ice. As each region rotates into sunlight, it produces a different kind of plume. These subtle changes create shifting waves within the coma and tail that carry with them the history of the material within the comet. During this stage, the comet reaches the part of its orbit where the solar wind begins to play a stronger role. The solar wind is a stream of charged particles flowing outward from the sun in a constant but gentle breeze. When these particles reach the comet, they interact with the gases emerging from its nucleus. This interaction creates a second tail formed of ionized gases that glow faintly under the sunlight. This ion tail is straight and narrow, always pointing directly away from the sun because it is shaped entirely by the flow of charged particles. As the comet moves closer, this tail becomes longer and more defined, revealing the strength of the solar wind at that moment in time. While all of this is happening, the dust tail continues to grow. Unlike the ion tail, which is shaped by the solar wind, the dust tail is shaped by the pressure of sunlight itself. Sunlight pushes dust particles outward and forms a broad, sweeping arc behind the comet. This tail curves slowly and gracefully, and its shape tells astronomers about the sizes of the grains released from the nucleus. Larger grains travel more slowly and form a thick core, while finer grains drift outward into a delicate veil. Through these tails, the sun writes the story of the comet's composition across the sky. At this distance from the sun, the nucleus begins to change physically. Sublimation removes surface layers, which can crack or break as pressure builds beneath them. Some comets experience large outbursts at this stage, though 3I Atlas remained mostly steady with only mild increases in brightness. Even so, the surface was evolving. Each jet and each plume carved new grooves into the crust. Each rotation brought new areas into sunlight and released more ancient material. Over time, the shape of the nucleus itself may have changed slightly, though these changes are too small to detect directly from Earth. The chemistry of the gases escaping from the nucleus reveals more about the comet's origins. Spectroscopic measurements show that the water content rises steadily as the comet approaches the sunday. The ratio of carbon dioxide to water decreases, but the total amount remains unusual compared to most solar system comets. This confirms that the comet formed in an environment where extremely cold conditions allowed large amounts of carbon dioxide to freeze and remain trapped. The sun is now warming these ancient ices and releasing them into space, where humans can study them for the first time. As the comet approaches even closer, the sunlight begins to penetrate deeper into the nucleus. The thermal wave moves slowly downward, reaching layers that have been preserved since the object first formed around another star. These layers contain complex organic molecules created in the early days of the comet's birth. When these molecules sublimate, they rise into the coma and become detectable by instruments in space. This allows astronomers to compare them with the organic molecules found in comets of our own solar system. These comparisons give insights into whether the chemical building blocks of life are common across different star systems. The slow heating from the sun also reveals the internal strength of the nucleus. Some comets are loosely bound collections of dust and ice that can fracture easily. Others are more compact and hold together strongly. 3I Atlas appears to fall somewhere in the middle. It shows signs of steady activity but no large breakups or violent disruptions. This stability allowed astronomers to gather consistent long-term data as it approached the Sunday. The steady release of gas and dust created clean, smooth lines in the brightness curve, which made it easier to model the internal processes taking place. Imagine yourself floating near the comet during this time. The sun shines brightly ahead, casting a golden light through the expanding coma. The dust particles glimmer faintly as they drift outward. The nucleus rotates slowly, and each turn brings a new fountain of gas into the light. The silence remains absolute. There is no sound of jets, no roar of gas, no echo of movement. Everything unfolds in perfect quiet. The only sensations are the slow drifting of dust, the steady glow of sunlight, and the ancient calmness of a body that has traveled across the galaxy to reach this moment. From Earth, the comet remains faint but deeply interesting. It is not a spectacle in the night sky, but rather a scientific treasure. Observatories record data around the clock. The brightness increases steadily, but never dramatically. The comet continues to respond to the sun in a measured, quiet way. Its changes are like the slow breathing of a sleeping creature, warming gently under the sun's touch. As the comet approaches perihelion, the point of closest distance to the sun, it enters the most intense phase of solar heating. In the next chapter, we will witness this moment. We will watch what happens when the sun finally reaches its full strength on the ancient surface of 3I Atlas. This is the moment when the deepest secrets of the comet begin to rise. For now, allow your breath to settle and imagine the comet drifting through a widening halo of light as it falls steadily toward the warmth ahead. The sun is waiting, and the journey continues with quiet grace. The moment of perihelion. Imagine the sun growing larger and brighter as 3I Atlas moves into the region of space where sunlight begins to feel almost physical. The golden glow becomes stronger, and the warmth reaches deeper into the icy nucleus. After billions of years wandering in cold darkness, the comet finally approaches the point of its orbit, where it will come closest to the Sunday. This moment is called perihelion. It is the most intense stage of the journey. Every comet experiences it in its own way, and for an interstellar comet, the moment feels even more profound, because nothing in its long history has brought it so near to any star since the day it first formed. As the distance shrinks, the sunlight becomes powerful enough to reach layers that were untouched for the entire lifetime of the comet. The temperature rises slowly but steadily. The nucleus responds with a deeper release of gas. Water vapor becomes the dominant molecule escaping from inside the comet. This shift marks a significant transition. The sun is now heating the comet enough to release the strong bonds of water ice. What rises from the surface now comes from the oldest frozen layers. These layers contain the most ancient material preserved from the original disk of dust and gas that formed another star system long before our sun was born. The coma grows wider as the inner ices sublime. The dust content rises as grains locked inside the ice are pushed free and carried outward. The tail becomes brighter in long exposure images, and extends farther across the sky. Astronomers can see the shape shifting as the nucleus rotates. Some jets fire more strongly when certain regions of the comet face the sunday. Others fade as they move into shadow. These changes reveal the uneven structure of the surface. Some areas are smooth, while others have deeper fractures, where sunlight finds easier pathways into the interior. The sun now becomes the main sculptor of the comet. Every hour, it reshapes the outer layers. The gas rising from the surface increases the internal pressure. On some comets, this stage can cause violent fragmentation, but 3I Atlas remains steady. Its body holds together under the growing heat. The release of gas is continuous and smooth. The dust cloud thickens. The comet brightens, but never dramatically. It chooses a quiet path, even under the strongest light it has ever experienced. Perihelion arrives like the peak of a long breath. At this moment, the comet is just over 1 astronomical unit from the Sun, a little farther than Earth's distance. The sunlight is intense. The thermal wave reaches into patterns of ice that have never melted before. The coma is at its largest, and the tails extend across millions of kilometers of space. The ion tail appears long and narrow. The dust tail bends gently as sunlight pushes the particles outward. Both tails stream steadily away from the sun as the comet continues to move along its hyperbolic path. During perihelion, the chemical signatures in the gas release reach their highest clarity. Instruments detect strong water vapor along with carbon dioxide and carbon monoxide. The ratios between them tell astronomers about the temperature conditions of the comet's birthplace. The high carbon dioxide content suggests a region far colder than the outer areas of our own solar system. The faint but persistent nickel signatures become clearer now. These metals rise from deeper layers, disturbed by the intense heating. They reveal a kind of mineral structure rarely seen in typical comets. The rotation of the nucleus helps scientists map the distribution of materials inside it. Each time the nucleus turns, a new jet faces the sun and releases its own unique chemical mixture. Over time, these repeating patterns allow astronomers to understand how the internal structure is arranged. Some regions contain more dust. Others contain thicker layers of volatile ice. Some regions respond quickly to sunlight. Others warm more slowly. The sun reveals these differences gently, but clearly, as the comet rotates under its light. Imagine drifting beside the comet at this moment. The sun fills the sky with soft golden light. The coma glows around you like a vast mist lit from within. Dust grains shimmer as they float away from the nucleus. Some are large and drift slowly. Others are tiny and dance in spirals pushed by the sunlight. The nucleus turns below you in complete silence, and every turn releases another soft plume of gas into the surrounding glow. The entire scene feels timeless and weightless. Nothing moves quickly. Nothing disturbs the stillness around the comet. Even the most powerful light in the solar system touches the surface with quiet persistence rather than violence. For astronomers on Earth, the comet remains faint but stable. It does not produce any spectacular outbursts. It does not break apart into fragments. It simply continues to sublimate at a steady rate. The brightness curve shows a calm peak near perihelion, followed by a slow decline. This behavior helps confirm the strength of the nucleus and the uniformity of its internal structure. The object may be fragile on the surface, but its deeper layers are well consolidated. This stability is unusual for a comet under strong heating, and it offers scientists a unique opportunity to study long-term changes without sudden interruptions. After the moment of perihelion passes, the comet begins to recede from the sunday. This is the turning point of the journey. The sun has reached into the deepest accessible layers. The peak heating has passed. Now the comet begins the long, graceful outward slide along its hyperbolic path. The gas production decreases slowly. The tails begin to thin. The coma starts to contract. The nucleus cools as each hour increases the distance. The sun still exerts influence, but the most intense stage is now behind it. Even as the comet moves away, the effects of perihelion remain visible. Dust released near perihelion lingers in a broad trail behind the comet. The ion tail continues to extend for some time, as long as gas remains in the surrounding space. The sun has shaped the comet fully for this passage. Its influence has revealed the chemistry, structure, and behavior of a body older than the solar system. What was once frozen in silence has now spoken through gas and dust. These signals have been captured by telescopes on Earth and in orbit. They will be studied for years to come. Imagine the feeling of the comet cooling slightly as it drifts outward. The gas jets soften. The light around it grows thinner. The coma becomes more transparent. The sun begins to shrink subtly in the sky. Yet even as the activity fades, the journey is not over. The outward path will reveal new details about how the nucleus settles after heating. In the next chapter, we will follow this cooling phase and watch how the comet transitions from its moment of maximum activity back into the quiet of deep space. For now, take a slow breath and imagine the glow of perihelion fading gently behind the comet as it begins to drift away from the sun once again. The long cooling after sunlight. Imagine the soft and gradual dimming that follows the moment of perihelion. 3I Atlas has passed its closest approach to the sun and now begins the slow outward journey into cooler space. The sun still shines behind it with steady warmth, but the intensity no longer reaches as deeply into the nucleus. The ancient surface, which had awakened under the strongest sunlight it had ever felt, now begins to rest once again. The gases that once rose freely from its interior start to decline. The jets grow softer. The tails grow thinner. Everything about the comet begins to quiet in the same slow way that dawn fades into morning. As the comet recedes, the temperature around the nucleus begins to fall. This change is gentle and gradual. The coma contracts slightly each day. The outer region of the coma becomes more transparent as the production of fresh gas decreases. Dust that was lifted earlier continues to drift away, forming long, faint streams behind the comet. The solar wind still shapes the ion tail, but the supply of new ions begins to fade. The ion tail becomes thinner and less bright. Eventually, it narrows into a quiet thread of gas that stretches into the dark. The nucleus itself cools from the outside inward. Layers that were heated during the approach now begin to freeze again. The thermal wave that penetrated deep during perihelion slowly retreats. As it moves inward, the remaining gases trapped in the near-surface layers condense. Some of these molecules freeze back onto the surface, forming thin coatings of frost on dust grains and exposed rock. This freeze-out process plays a quiet role in shaping the comet's surface for its long future journey. Some jet vents will seal. Some fractures will close. Some regions will remain open for a while. The sun has changed the outer layers permanently, but the deeper structure begins returning to its natural cold. During this cooling stage, astronomers observe the emerging patterns closely. They measure how quickly the gas production decreases. They take spectroscopic readings to understand which molecules linger longest. They track the brightness of the coma to see if any late outbursts occur. 3I Atlas continues to behave in a calm and predictable way. No sudden events disturb the surface. No massive chunks break loose. It simply releases less and less material as the distance increases. The slow fading tells scientists about the strength and thermal behavior of the nucleus. A truly fragile object would have fractured under the sudden withdrawal of heat. But this comet continues its journey with gentle steadiness. Imagine the comet now drifting outward with a faint halo of light surrounding it. The golden brightness of perihelion is behind it. Ahead lies a path into cooler and quieter regions. The activity that once defined the comet now becomes a soft whisper. The dust tail begins to disperse as the comet's forward motion carries it deeper into space. The largest particles lag behind, forming a curved trail that marks the path it traveled. This dust will continue drifting across the solar system for years, perhaps even decades, forming part of the slow, unseen circulation of material that surrounds the Sunday. The coma continues to thin until it is only a faint glow hugging the nucleus. If you could float beside it, you would see a small, dark core surrounded by a pale mist. The mist shifts gently in the sunlight, then slowly fades as the amount of gas decreases further. The sun now looks smaller once again. The shadows on the nucleus grow deeper as the brightness falls away. The comet begins to look more like the silent object it once was in interstellar space, though not entirely. The outer layers now carry the marks of their encounter with the Sunday. The pores are wider. The fractures are deeper. Some surfaces have been freshly carved by escaping gas. It is still the same ancient body, but now shaped by the warmth of a star it will never return to. Astronomers watch the gradual fading with quiet attention. This phase is as important as the approach. It tells them how the comet stabilizes after heating. It shows how the internal reservoirs of gas behave as the temperature declines. Some comets erupt one last time during this stage due to trapped pockets of pressure, but 3I Atlas remains steady. It releases its gases calmly and then slows in its activity. The brightness curve shows a smooth downward line. The slowing of sublimation offers a final look at the deep chemical relationships inside the nucleus. Even as activity fades, scientists can still detect faint traces of water vapor, carbon dioxide, and carbon monoxide. These fading signals help refine models of how heat moves through small icy bodies. Imagine drifting beside the comet as the sun becomes smaller in the sky. The warmth fades from the surface. The jets sigh into silence. The glow dims. The comet seems to relax into a familiar coldness. Slowly, a feeling returns that has accompanied the object for billions of years. It is the feeling of deep space, the calmness of darkness, the quiet of a journey with no destination and no return. The coma becomes nearly invisible. The nucleus grows colder each day. It is becoming an interstellar traveler once again. During this time, the orbit also reveals something meaningful. Because the comet is unbound, it continues to follow its hyperbolic path outward. It does not loop back toward the Sunday. The gravitational pull weakens behind it, and the comet moves steadily away with no intention of slowing. Its speed remains above the escape threshold. While planets and asteroids and long-period comets remain tied to the Sun, this object joins the rare few that come only once. Its journey near the Sun is a brief chapter in an enormous cosmic story. Imagine now that the comet has traveled beyond the region of Mars and continues outward with a dimming tail. The Sun grows ever fainter. The thermal energy inside the nucleus retreats deeper and deeper until every active layer becomes cold and still. The comet is returning to the condition it knew for most of its existence. A small, dark body drifting through the endless gulf of space, carrying within it the unchanged memories of its formation. The cooling period marks the quiet beginning of the comet's departure. In the next chapter, we will follow the gradual fading as 3I Atlas prepares to leave the solar system entirely. Soon it will cross the boundary, where the sun's influence becomes almost nothing. It will enter once again the deep silence between the stars. For now, take a calm breath and imagine the comet drifting slowly into the cooling distance as the warmth of the sun recedes behind it. The slow departure from the solar system. Imagine 3I Atlas drifting steadily outward, with the sun shrinking slowly behind it. The moment of perihelion is now far in the past. The comet carries the warmth of that moment only in fading memory. Each hour that passes carries it deeper into cooler regions. The coma that once glowed with soft light thins into a faint haze. The tails that once stretched across millions of kilometers begin to dissolve into the darkness. The comet moves quietly and without effort, following the path that gravity set long before humans ever looked toward the sky. As the distance increases, the sunlight weakens. The nucleus cools more deeply and the last pockets of activity soften into silence. Small jets that once released ancient gases now lie dormant. The fractures on the surface begin to freeze shut as temperatures fall. Thin layers of frost form over exposed dust. The comet begins to resemble the silent object it was during its long travels through interstellar space. The bright signature of its encounter with the sun fades away, and what remains is a calm, dark body returning to the cold. Astronomers continue to watch the fading of the comet, even as it becomes more difficult to detect. Telescopes gather what little light still reaches Earth. The brightness decreases steadily. The coma contracts until it becomes almost invisible. All that remains visible is the small nucleus reflecting a tiny amount of sunlight. Observers measure its fading with care because this stage tells them how quickly the surface returns to thermal equilibrium. The rate of cooling helps scientists understand the size and density of the nucleus. 3I Atlas cools smoothly, suggesting a compact but not overly dense structure. It is stable even after the intense heating of perihelion. Imagine looking at the comet from a spacecraft, drifting quietly nearby. The sun glows far behind it as a soft star rather than a radiant sphere. The nucleus lies ahead, small and dark, with only the faintest mist around it. The surrounding space feels deep and endless. There is no sound, no wind, no presence, except the slow outward motion of the comet and the distant warmth of the Sunday. In this silent moment, the comet feels as if it is sliding into its natural home, away from heat and light, back toward the calm emptiness where it spent almost all of its life. As the comet moves beyond the orbit of Mars, the final traces of its activity disappear. A gentle line of dust remains behind it, marking the path it traveled, but even this will disperse over time. The ion tail fades completely because there is no longer enough gas to generate charged particles. The dust tail loses definition and becomes a loose stream of grains drifting along the comet's trajectory. The sun continues shrinking, and the comet cools until its internal temperature returns to near interstellar levels. During this phase, scientists refine their measurements of the orbit. The comet's speed remains above escape velocity. It is clear that the object will never return. Unlike the comets that orbit the sun in long, slow loops, 3I Atlas belongs to another world. Its path is not a circle or an ellipse, but a single curve that enters the solar system once and then leaves forever. This shape is the quiet signature of an interstellar traveler. It arrived briefly. It revealed its ancient chemistry. It responded to our Sunday, and now it continues on into the dark. Imagine drifting farther from the comet now. It becomes a small point of light slowly moving away. The sun becomes a steady glow behind both you and the comet. Between the two of you lies a growing distance. The universe around is silent and wide. Stars flicker gently across the sky. This is the realm where 3I Atlas will spend the rest of its journey. It will leave behind the planets and the warmth and the solar wind. It will leave behind every place where humans can watch it. As it moves farther outward, the influence of the sun weakens steadily. Gravity still pulls, but the comet is too fast to be held. Eventually, it reaches a region where the solar wind becomes faint and the density of particles drops sharply. This is the outer boundary of the heliosphere, the region shaped by the sun's magnetic field and flowing particles. Beyond this lies interstellar space. Not a solid wall, not a sudden boundary, but a gradual change in the environment. The comet drifts toward this boundary with complete calm. Inside the heliosphere, particles flow outward from the Sunday. Outside it, particles flow inward from the galaxy. As the comet approaches this region, the pressure of the solar wind that once shaped its tail becomes nearly zero. Dust grains released earlier no longer feel the push of the Sunday. They drift independently, the way dust moves in deep space. The comet becomes a small, dark object again. It carries only the scars left by sunlight and the faint frost that has returned to its surface. Imagine being beside the comet as it moves through this threshold. There is no visible sign of the boundary. The stars look the same, the darkness looks the same. Yet the physics surrounding the comet changes. The stream of solar particles fades, the magnetic influence weakens. The environment becomes dominated by the quiet presence of the galaxy rather than the Sunday. In this gentle transition, the comet re-enters the domain where most of its life was spent. Astronomers will continue tracking the comet for as long as it remains detectable, but eventually it will grow too faint. There will come a day when it no longer registers on telescopes. It will continue its journey unseen. It will drift away from the solar system into the vastness between the stars. Its speed will carry it ever outward. Its path will bend slightly due to the gravity of passing stars and clouds, but nothing will pull it back. It will continue moving for millions of years in a direction no one can predict beyond a certain distance. Imagine the last moment when humans can observe the comet. The faint point of light that once marked an interstellar traveler becomes indistinguishable from the stars. Slowly it disappears from instruments, and no one knows its location anymore. It becomes once more what it was for most of eternity, a silent wanderer traveling alone through the galaxy. In the next chapter, we will follow the idea of this long interstellar journey and how the galaxy itself shapes the path of such an ancient traveler. For now, take a calm breath and imagine the comet drifting into the cool distance with the sun shrinking softly behind it. The return to interstellar night. Imagine the comet passing the final edge of the sun's influence. The light is now faint and gentle, and the warmth that once reached deep into its nucleus has faded into memory. 3. Atlas is slipping back into the realm where it came from, the wide open dark between the stars. This is not a sudden shift. There is no boundary line or visible doorway. The solar wind simply weakens until it can no longer shape the space around the comet. The magnetic field of the sun no longer reaches it with strength. The environment slowly becomes the quiet, cold, drifting place the comet has known for almost its entire existence. As 3I Atlas moves outward, the stars around it shine with soft clarity. Without the solar glare, the view becomes crisp and deep. The galaxy stretches in all directions as a faint glowing band. The Milky Way surrounds the comet with the same calm beauty it has always known. The nucleus cools completely. Any remaining vapor settles back into tiny patches of frost. The cracks that opened under the heat of perihelion freeze into stillness. No gas escapes now. No dust lifts from the surface. The comet becomes quiet in a way that feels ancient and familiar. The path of the comet continues to widen as it moves away from the Sunday. Its hyperbolic trajectory leads it outward in a smooth curve. It will never turn back. The sun has no more hold on it. Gravity grows weaker behind it with every passing day. Ahead of it lies a long journey through the galactic neighborhood. It will pass through regions of thin gas. It will pass near stars that shine from great distances. It may drift through gentle clouds of interstellar dust, but nothing will significantly change its direction for a very long time. The path is calm and slow and stretches across millions of years. Imagine drifting beside the comet as it enters a region where the sun is only one star among many. Seen from here, the sun no longer dominates the sky. It appears as a bright point with no halo. It is a single star glowing in the darkness. The planets that circle it are invisible at this distance. The entire solar system becomes nothing more than a small point of light behind the comet. Ahead lies the quiet of the galaxy. Space feels wider here. The silence is deeper. The darkness is softer. The true environment of interstellar space now surrounds the comet. This region is filled with extremely thin gas, mostly hydrogen atoms, drifting far apart. Occasionally, a dust grain floats through the emptiness. Radiation from distant stars passes freely. The temperature drops to just a few degrees above absolute zero. Yet the comet is comfortable in this cold. It was formed in such conditions. It has spent almost all of its life here. The brief passage near the sun was only a warm interruption in its endless journey. Scientists on Earth continue to refine their models of the comet's future path. They know that its motion is shaped not only by the sun, but also by the combined gravity of the galaxy itself. Over millions of years, the comet will move through the galactic disk. It will feel tiny pulls from passing stars. It will drift through spiral arms where gas clouds are thicker. It may pass close enough to a distant star to be nudged into a slightly different direction. But these changes are gentle and happen over timescales far beyond human lifetimes. Imagine the comet traveling through this quiet environment. The stars drift slowly relative to its motion. Some stars shine brighter for a moment as the comet moves closer to them, then fade again as it moves past. The galaxy does not rush. Everything here happens slowly and calmly. The comet glides through this darkness the way a leaf floats on a still lake. Nothing disturbs its path. The silence is complete. Far ahead, the comet will pass through regions filled with cosmic rays. These high-energy particles travel through the galaxy at nearly the speed of light. They will strike the comet's surface one by one. Each impact will slowly change the outer layers over millions of years. Atoms will be rearranged. Molecules will be altered. The surface will darken even more, but the interior will remain unchanged. Deep inside the nucleus lies the ancient material that records the history of the star system where the comet was born. This information will stay preserved for billions of years. Imagine the comet a million years from now. It is far from the Sunday. It has crossed regions humans will never see. The stars around it have shifted. Entire constellations look different. The sun remains just one star, lost in the brightness of the Milky Way. The comet continues forward without knowing where it goes, without needing to know. It drifts through the galactic plane toward regions where other stars lie waiting with their own planets and their own cometary clouds. Perhaps one distant day the comet might pass near a star and be drawn into a new system. Perhaps it will approach another sun the way it approached ours and awaken once again. When that happens, it will warm and glow just as it did near the Sunday. It will release gas and dust that has been preserved for ages. Another civilization on another world may then observe it with curiosity. They may study its composition. They may wonder where it came from. They may see it as a visitor from a place long forgotten. The comet will not remember us, but humans will remember it as one of the rare messengers between stars. Imagine 3i Atlas settling into the endless quiet. The sun is long behind it. The galaxy stretches ahead. There is no rush, no destination, only motion through soft darkness. The long journey continues without sound, without light, except for the faint glow of distant stars. In this calm, returning silence, the comet becomes once more what it has always been, a wanderer between suns, a traveler shaped by ice and time, a visitor carrying the ancient story of another world into the deep, unending night. The galactic drift through time. Imagine 3i Atlas gliding through the galaxy as if time itself has slowed. The comet is far beyond the reach of the sun now. The faint warmth that touched its surface during perihelion is gone. It has entered a realm where distances are measured not in kilometers, but in light years, and where change unfolds over spans longer than civilizations. The comet moves without effort. It simply follows the gentle curvature of the galactic gravitational field as it drifts through a sea of stars. As 3i Atlas travels deeper into interstellar space, the sun becomes just one pale point behind it. The stars around the comet no longer appear fixed. Over long stretches of time, they drift past like glowing islands. Their positions change, one by one, as the comet moves through the galaxy's spiral arm. This motion is slow and quiet, but it never stops. The galaxy rotates. Stars migrate. Clouds of gas shift gently. Through all of this motion, the comet continues its patient journey. Inside the nucleus, the temperature remains near absolute zero. The materials that once warmed during perihelion are now frozen harder than stone. The outer layers darken over time as cosmic rays strike the surface. These rays come from supernova explosions and distant astrophysical events. They pass through space with enormous energy, and when they touch the comet, they alter molecules one by one. The modifications are tiny, but over millions of years, the surface loses brightness. It becomes a deep charcoal black, yet the core remains unchanged. The interior still holds its ancient chemistry intact and untouched. Imagine drifting beside the comet as it moves through a region filled with faint starlight. The Milky Way stretches like a band of dust and fire across the darkness. Stars shine with slow confidence. Some are red and dim, others are blue and bright. Some are giants nearing the end of their lives. Some are newborns just emerging from dense clouds. All of them remain far away. The space between them is enormous. The comet glides through this stillness with a calmness that feels older than time. Occasionally, the comet will pass near a region where the density of gas is slightly higher, not enough to disturb its path, but enough to create a faint whisper of resistance as it moves through the thin material. These regions are not dangerous. They are simply part of the galactic environment. The comet may pass through a gentle haze of hydrogen atoms or drift through a sparse cloud of dust grains. None of these encounters change its course in any meaningful way. The forces involved are too small, and the distances too immense. The next major influence on the comet's path will not come from gas, but from stars. A close pass with a distant star can deflect comets by a tiny amount. These encounters are rare and happen slowly. But 3I Atlas will experience many over the course of millions of years. Each encounter will add a slight bend to its path. The changes are subtle but cumulative. Over vast timescales, the comet's trajectory may shift enough that it enters a different part of the galaxy. It may drift closer to the thick spiral arms where new stars are born, or move outward toward the fainter regions near the galaxy's edge. Imagine the comet tens of millions of years from now. The sun is long gone from view, lost among countless other stars. The galaxy around the comet has changed. Spiral arms have rotated. New stars have formed. Some have died. Whatever planets once existed around distant suns may be gone or replaced by new ones. Civilizations may rise and fall on worlds we will never know. Through all of this, the comet continues moving. It keeps no record of the changing galaxy. It simply follows the pull of gravity with perfect patience. Perhaps one day, it will pass close enough to a star for that star's gravity to take hold. If the encounter is strong enough, the comet may be captured into a new orbit. It might become part of another star's cometary cloud. It could drift into a region where it will one day pass near another sun and awaken once more. If that happens, its frozen core will warm again. Its coma will bloom into light. Its tail will stretch across space. The gases inside it will carry the chemistry of two different star systems through the galaxy. Another world may then observe it and wonder where it came from, just as humans once wondered about it. But it is just as likely that the comet will continue drifting freely for billions of years without ever being captured. Many interstellar objects travel the galaxy without belonging to any star. They drift in an endless night, shaped only by the gravity of the Milky Way. They remain unbound forever. 3I Atlas may be one of these eternal wanderers. If so, it will spend the rest of cosmic history slipping through the galaxy like a soft shadow, a relic of a time long past, a messenger from a place no longer known. Imagine the comet a billion years from now. Stars have shifted completely. The spiral arms of the galaxy have moved. The sun has changed, and perhaps no longer exists in its familiar form. Yet the comet continues its quiet path. It is still cold, still dark, still unchanged in its core, still carrying the ancient materials of a star system that once gave it life. It has no destination. It has no purpose. but it carries the history of worlds written in ice. In the next chapter, we will explore the ancient chemistry inside 3I Atlas and what it tells us about the place where it was born. For now, take a calm breath and imagine the comet gliding through the galaxy in perfect silence, the stars drifting slowly around it as time stretches on without end. The ancient chemistry inside the wanderer. Imagine drifting into the inner heart of 3I Atlas, as if its layers could open like a quiet doorway. Deep inside the nucleus lies a world that has remained frozen for billions of years. The warmth of the sun reached only the surface and the shallow layers just beneath it. Everything deeper remained untouched. This interior holds the chemistry of another star system. Nothing else in the solar system shares this exact composition because the comet was shaped far away long before our sun had even formed. It is a time capsule from a distant origin. The core is made of ices that formed in temperatures only a few degrees above absolute zero. These ices contain water, frozen harder than stone. They also contain carbon monoxide and carbon dioxide, mixed with dust grains that came from the disk of material surrounding a young star. Just as our solar system formed from a swirling cloud of gas and dust, the star system that created this comet also produced hundreds or thousands of icy bodies. One of them eventually escaped into interstellar space and after an unimaginable journey arrived near the Sunday. Inside the nucleus, the dust particles tell a quiet story. Some grains are older than the comet itself. They are tiny fragments of ancient stars. They formed in the dying atmospheres of red giants, or in the explosive shockwaves of supernovae. These grains drifted through clouds of gas until they became part of the system that created 3I Atlas. When astronomers study the dust released from the comet, they detect signatures of these ancient stars. The minerals contain traces of magnesium and iron and nickel in unusual ratios. These patterns reveal a birthplace colder and more distant than the early outer regions of our solar system. Imagine the ice inside the comet as a vast crystal structure. Inside this frozen structure are small pockets where molecules became trapped. Some are simple, such as carbon monoxide and methane. Others are more complex. Comets often contain traces of organic molecules. These molecules are not alive, but they are the building blocks of life. They include simple alcohols and acids and long carbon chains that can combine into more complex chemistry. When the sun warmed 3I Atlas during perihelion, these molecules rose from the nucleus and revealed themselves in the coma. The ratios between different gases give scientists clues about the environment where the comet was formed. The high abundance of carbon dioxide relative to water suggests an origin in extremely cold regions. The detection of metals like nickel in the gas phase suggests unusual thermal processing before the comet solidified. These clues point toward a system different from our own. Perhaps the comet came from a young star with a dimmer light, or from a region farther from its sun than Pluto is from ours. Every molecule released from the comet is a message from that long-lost world. Imagine holding a single grain of dust from the comet. It is no larger than a grain of sand, yet it contains the history of stars. It holds patterns created in furnaces hotter than anything the sun can produce. It carries within it atoms forged in the earliest generations of the galaxy. When such grains are found in meteorites on Earth, they help scientists understand the long chain of events that created planets and life. But in an interstellar comet, the grains come from a different lineage. They come from a world we will never see. The ice inside the comet also contains isotopes that act like fingerprints. By studying ratios of heavy hydrogen to normal hydrogen, astronomers can compare the water in the comet to the water in Earth's oceans. Long-period comets from our solar system show certain patterns, but interstellar comets often show different ones. These differences tell scientists that the chemistry of distant star systems can vary widely. 3I Atlas carries its own unique pattern, one that reflects the environment of its birth. Deep inside the nucleus, the ices have never melted. they have not been exposed to sunlight since the comet left its original star system. The molecules remain arranged in the same patterns they held when the comet was young. This preserved interior may be billions of years old. It may be older than the Sunday. It may contain records of processes that happened before our solar system even existed. As the comet drifts through interstellar space, these molecules remain locked away, cold and silent and unchanged. Imagine drifting deeper into the core. You would find pockets of trapped gases, frozen in place. You would find layers of dust, embedded in ice, like pages in a book. Each layer records a different moment in the history of the comet's formation. Some layers contain more organic material, others contain more minerals. The structure reveals a slow, gradual building process as ices and dust accumulated around the growing nucleus. Nothing about this formation required heat or pressure. It happened quietly in the dark as particles stuck together over millions of years. When the comet approached the sun, it opened a brief window into this internal world. The gases that escaped during perihelion allowed scientists to study the chemistry of the comet without cutting into it. These gases revealed patterns that no solar system comet shares. They confirmed once again that the comet came from another star system. This interstellar signature makes 3I Atlas a rare visitor. It carries information that cannot be found anywhere else in the solar system. Imagine now that the comet is far beyond the sun once again. The chemistry inside remains preserved for the future. No heat will reach the core for millions of years. Perhaps the comet will awaken again near another star. When that moment comes, the molecules inside it will rise into space once more. Astronomers of another world may then detect its unusual chemistry and wonder where it came from. They may realize that the comet came from a distant system and carries the story of a star that no longer exists or has changed beyond recognition. The inner chemistry of 3I Atlas is more than frozen material. It is a memory carved in ice. It is a record of a place and time that the comet itself has long traveled beyond. It is the silent message of another world, written in the simplest building blocks of matter. As we continue the documentary, we will explore how these building blocks may relate to the earliest stages of life, and how comets may have carried similar materials to young planets. For now, imagine the ancient chemistry of the comet, resting quietly in the dark as it drifts through interstellar space, unchanged and eternal. How comets carry the seeds of life. Imagine the core of 3I Atlas drifting through the dark with the chemicals inside it held in perfect stillness. These chemicals are simple, yet powerful. They are not alive, but they are the ingredients from which life can emerge under the right conditions. Scientists call them prebiotic molecules. These molecules form in the coldest and darkest regions of space long before planets exist. They attach themselves to tiny grains of dust and become part of icy bodies like comets. When these comets travel near stars, they release these molecules into space and sometimes deliver them to young planets. The chemistry inside 3I Atlas includes simple alcohols and small organic acids. These molecules form when atoms meet on the surface of dust grains in space. Hydrogen settles onto oxygen and forms water. Carbon combines with oxygen and creates carbon dioxide. Under the cold of interstellar space, these molecules can link into chains. These chains can become the basic structures needed for more complex chemistry. Scientists have found traces of these molecules in many comets, but the mixture inside an interstellar comet is especially interesting because it formed under conditions different from our solar system. Imagine a young planet forming around a new star. Its surface is hot at first, and then it cools into oceans and land. Comets may strike this world and release their ices into the warm environment. When those ices melt, the organic molecules become part of the planet's water. Over time, they may combine into even more complex structures. Many scientists believe that comets brought these building blocks to Earth during its early history. They believe that the oceans of Earth may have been enriched by cometary material. This idea does not say that comets created life. Instead, it suggests that comets delivered ingredients that life later used. 3I Atlas carries these same building blocks. It has drifted through the galaxy for millions or even billions of years, with these molecules protected inside its frozen core. When the comet passed near the Sun, a small amount of this ancient chemistry escaped into the coma. Astronomers detected traces of organic molecules in the gas cloud. Even though the comet was faint and not easily observed, the signatures were strong enough to show that the comet held a mixture of prebiotic compounds. These molecules survived the long journey across interstellar space and the brief warming near our Sunday. Imagine the comet approaching a young world far in the future. If the world has oceans, the heat of entry may melt the comet's ice. The organic materials inside could spill into the water and drift across the planet's surface. These molecules could mix with minerals and form new compounds. Under the right conditions, they could become part of the slow unfolding of life. It is a quiet possibility, and one that echoes through the history of the galaxy. Comets may have served as carriers between worlds long before any life existed to notice. The dust grains inside 3I Atlas also contain complex carbon structures. These grains formed in the atmospheres of old stars and were carried into the cloud that created the comet's original system. When these grains mix with water and heat, they can become part of chemical reactions that lead toward amino acids and other important molecules. The presence of these grains inside the comet shows that interstellar environments naturally create the ingredients needed for life, even without planets or suns. Chemistry in space is slow, but patient. Over millions of years, even simple molecules can become more complex. Imagine drifting within the comet's nucleus as it forms in its original star system. Dust grains settle together quietly. Thin layers of ice grow over them. The molecular structure becomes more intricate as atoms slowly find each other. No light shines here. No warmth guides the reactions. Everything happens through contact at the smallest scale. Yet this calm process builds the foundation for future chemistry. When scientists study the gases released from comets, they see the fingerprints of these early reactions, and they learn how organic chemistry begins in deep space. The fact that 3I Atlas contains these molecules suggests that many star systems across the galaxy may create the same basic ingredients. Life on Earth may not be unique in its chemical foundation. It may share this foundation with countless other worlds. The building blocks of life appear to be common in regions where stars form. They appear to be part of the natural processes of the galaxy. Comets like 3I Atlas are quiet carriers moving these ingredients between systems. Imagine the comet millions of years from now. It may pass near a cloud where new stars are forming. It may drift into a region filled with young planets and warm light. It may be drawn close to another star. When that happens, its surface will warm once again. The ice will release gas and dust into space. The ancient molecules inside will rise and drift through the new system. They may fall onto a young planet. They may join oceans or mix with minerals. They may take part in chemical processes that unfold into something new. 3I Atlas does not aim to deliver life. It simply carries the early ingredients across the galaxy. It has done so for longer than human history. It will continue to do so long after the Earth's story is finished. This quiet transport of organic material is one of the ways the galaxy spreads the elements needed for life. It happens slowly and silently through comets like this one. In the next chapter, we will explore how interstellar comets help scientists understand the formation of other star systems. For now, imagine the ancient molecules inside 3I Atlas, resting in perfect stillness as the comet drifts through the dark, carrying the seeds of possibility across the depths of space. What interstellar comets reveal about other star systems? Imagine 3I Atlas drifting far beyond the sun while carrying the quiet secrets of the place where it was born. The comet is not only a wanderer, it is also a messenger. Its chemistry and structure hold clues that help scientists understand how other star systems form material and evolve. Each molecule released near the Sun acted like a small fragment of a distant world. When astronomers detected these fragments, they opened a window into the conditions that existed around a young star long before our own solar system existed. The gases released by 3I Atlas showed an unusual balance between water, carbon dioxide, and carbon monoxide. These ratios are different from those found in the majority of comets that formed in our solar system. Such differences reveal that the comet formed in a much colder region than the birthplace of most long-period comets here. They suggest a disk of gas and dust around its original star that was colder, dimmer, or farther from the star's warmth. These insights allow scientists to model other planetary systems with greater accuracy. Each measurement helps fill in a larger picture of how stars across the galaxy build their icy bodies. Imagine looking at a newborn star wrapped in a swirling disk of gas and dust. Tiny grains collide and stick together, forming the earliest structures of planets and comets. The temperature in this disk changes with distance from the star. Warm regions produce rocky planets. Cold regions produce icy worlds. The specific chemistry of the ices depends on how cold the disk is and how much radiation flows through it. The unusual chemistry of 3I Atlas tells scientists that its disk had unique conditions. It may have been part of a young star that emitted less heat, or part of a broader disk farther from the star than typical comets around the Sunday. The presence of certain metals in the comet's gas cloud also tells scientists about the dust grains in the original star system. Traces of nickel detected in the gas reveal that grains with metallic content were trapped inside the comet when it formed. These grains may have come from supernova remnants that seeded the cloud of gas from which the star system formed. Every star system begins with a mixture of material produced by earlier generations of stars. By studying comets like 3I Atlas, scientists can trace these materials back to their sources. Imagine the star system where the comet was born. It may have had planets forming at the same time. Some may have been rocky worlds. Some may have been gas giants. All of them would have interacted with the disk in different ways. Some planets might have scattered icy bodies outward through gravitational encounters. Over time, one of those encounters may have been strong enough to eject 3I Atlas from the system entirely. Once the comet escaped the star's gravity, it drifted into the galaxy and began its long interstellar journey. The process that launched it is the same process that may launch comets from thousands of other star systems scattered across the Milky Way. When the comet reached our solar system, its trajectory revealed that it was not bound to the Sunday. Its hyperbolic path told astronomers that it was an interstellar visitor. This information helped scientists refine models of how often such objects pass through the solar system. Before the first known interstellar comet was observed, many believed these visitors were rare. Now we know that countless comets wander the galaxy between stars. Many have passed through the solar system without being detected. 3I Atlas became part of this growing evidence that interstellar comets may be common. Imagine that the galaxy is filled with millions of silent travelers like this one. Each carries the chemical story of its birthplace. Each holds records of temperature, pressure, and radiation from a different time and place. When any of these comets pass near a star, they reveal a little of this story in their gas and dust. Scientists collect that information and use it to compare different star systems. In this way, interstellar comets help build a broader understanding of how the galaxy creates and recycles matter. The shape of the nucleus also provides information. Even though scientists cannot see the nucleus directly, its rotation and outgassing patterns reveal its structure. 3I Atlas showed signs of an uneven surface shaped by billions of years of cosmic rays and gentle collisions. Its stability near perihelion suggests a compact interior rather than a loose rubble pile. This stability offers clues about how icy bodies clump together in other star systems. It appears that the processes that shape comets around distant stars may be similar to those in our own system, but with small differences influenced by local conditions. Imagine the comet deep in the galaxy, long after passing the Sunday. It carries these silent records inside its frozen layers. No one can read them now, but they remain intact. The comet will drift through space with these memories preserved. If it ever encounters another star system, these signals will reveal themselves again to new observers. They may study the comet and learn about the world where it began. They may see its chemical patterns and understand the conditions of its ancient home. The story of 3I Atlas is not only the story of a single object, it is part of the larger story of how matter moves between stars and how every star system influences others. The comet links distant regions of the galaxy. It shows that star systems are not isolated worlds, but part of a shared environment filled with drifting material. This material carries clues from one world to another quietly and endlessly. In the next chapter, we will explore how interstellar comets challenge our understanding of planetary formation and why they may be more common than once believed. For now, imagine the comet carrying the silent fingerprints of another star system as it drifts deeper into the galaxy and the darkness grows softer around it. Why interstellar comets may be common in the galaxy. Imagine the Milky Way as a vast ocean filled with currents you cannot see. Stars drift slowly around its center. Planets orbit those stars. And scattered throughout this ocean are countless icy bodies like 3I Atlas. These bodies do not belong to any star. They move freely through the galaxy following long, gentle paths shaped by gravity. For a long time, scientists believed that interstellar comets were rare visitors, but discoveries in recent years have changed that view. Every new object adds evidence that the galaxy may be filled with wandering comets. When 3I Atlas entered the solar system, its orbit revealed immediately that it was not bound to the Sunday. Its speed was too high. Its path was too curved and open. These signatures confirmed an interstellar origin. Only 2 interstellar visitors had been observed before it. But scientists realized that detection was the limiting factor. Objects like these are small, faint, and fast. They often pass through the solar system without being seen. Much of the time, they never come close enough to reflect enough sunlight for detection. Imagine a star system forming in a cold region of space. As planets grow, they scatter countless icy bodies outward. Some are pulled into long orbits. Some fall inward toward the star. But many are ejected completely. Gravity gives them a push strong enough to escape the system forever. These ejections happen in every star system where planets form. The galaxy contains hundreds of billions of stars. Even if each star ejects only a small fraction of the comets that form around it, the total number of interstellar comets becomes enormous. Over time, these objects fill the galaxy like dust in a beam of light. 3I Atlas is one of these ancient wanderers. It carries the chemistry of its original system and the record of its journey. When scientists modeled the likely number of such objects, they found something surprising. The galaxy may contain more rogue comets than comets bound to individual stars. These interstellar bodies drift quietly between systems. Some pass near stars and awaken in a sudden burst of activity. Others remain dark and frozen for all of time. Most never encounter another star closely enough to warm them. But a few, like 3I Atlas, pass near suns and reveal themselves. Imagine the galaxy with countless faint objects moving silently through its spiral arms. Most are smaller than a mountain. Many are covered in dark organic material that hides them from view. Only when they come close to a star do they emit gas and dust and become visible. 3I Atlas did exactly that. Its short display near the sun offered scientists a rare glimpse into the population of interstellar bodies that drift through the Milky Way. These objects may hold clues about how common planetary systems are. If interstellar comets are numerous, it suggests that planet formation is efficient. It suggests that many young planets scatter icy debris outward as they migrate through their disks. This scattering produces the quiet drift of material between star systems. The frequency of interstellar visitors, like 3I Atlas, supports the idea that planetary systems across the galaxy may be common and diverse. Imagine standing on a quiet hillside at night on Earth. The stars above appear steady and still, yet the space between them is alive with motion. Something small and dark may be passing overhead at this very moment. It may be drifting through the solar system on a path that began around a star you cannot see. It may be a silent interstellar comet too faint to detect. This idea changes the way astronomers see the galaxy. Instead of a collection of isolated star systems, the galaxy becomes a connected environment where icy travelers move freely. 3I Atlas may not be unique. It may be one of countless forgotten bodies that escaped from distant suns. Some may pass the sun in the future. Some may have passed long before humans existed. Some may carry chemistry very different from anything found here. Others may resemble the comets we know. Each wanderer is a sample of conditions from faraway planetary nurseries. Together, they help scientists understand the range of environments in which comets can form. Imagine the comet now drifting deeper into the galaxy. It is one among many. Behind it lie the countless paths of other wanderers. Ahead lie unknown regions where more may be drifting through the dark. None of these comets know each other. They follow their quiet paths without purpose. Yet together, they help shape a larger story. They show that the galaxy is active and interconnected. They show that stars exchange material not through direct contact, but through slow, steady drifting that unfolds over billions of years. The presence of interstellar comets also shapes ideas about how life may spread. If simple organic molecules are common in these objects, then the seeds of life may be traveling through the galaxy as well. Some may fall onto young planets. Some may remain frozen in space. Some may never reach a place where they can influence new chemistry. But the possibility exists that life's earliest ingredients do not remain confined to individual star systems. 3I Atlas is one piece of this cosmic puzzle. Its journey through the solar system provided a glimpse into the vast population of interstellar wanderers. In the next chapter, we will explore how gravitational forces ejected the comet from its original system and how these processes connect planetary formation events across the galaxy. For now, imagine the comet drifting through a quiet sea of other unseen wanderers, all moving slowly through the endless night. The moment a world lost the comet. Imagine the comet long before it ever came near the Sunday. Imagine it as a small icy body orbiting a distant star in a young and crowded system. That system was alive with movement. New planets were forming. Dust swirled in thick clouds. Gas drifted in soft spirals toward the newborn star. Everything was shifting and colliding. The comet was just one of countless icy fragments building the outer regions of that system. For a quiet period, it moved in a stable orbit, far from its star. Nothing disturbed it. It remained cold, dark, and peaceful. Then, something changed. In young star systems, planets do not always stay where they first form. Giant planets often migrate inward or outward. Their movement through the disk of gas creates gravitational waves that spread across the system. These waves scatter small objects like comets. Some are pushed into new orbits. Some fall inward toward the star. Others are thrown outward into deep space. The comet that would become 3I Atlas was one of those objects caught in this slow but powerful motion. Imagine a giant planet drifting slightly inward as gas flows around it. Its gravity reaches far into the system and disturbs the orbits of icy bodies at the edge. The comet feels a gentle pull first. Its orbit becomes a little wider. Then it receives another nudge, and another. Over thousands of years, these small nudges build into a larger change. The comet is slowly removed from its original quiet path. It begins to wander farther from the star each time it completes an orbit. The gravitational pushes continue until eventually one encounter becomes strong enough to free it completely. This final encounter may have been with a giant planet or with another large icy body. The paths of two objects can cross at just the right moment for gravity to act like a slingshot. When this happens, the smaller body gains speed and is launched outward. For 3I Atlas, this moment marked the beginning of its interstellar journey. One instant, it belonged to a star system. The next, it was free from it forever. It crossed the invisible boundary where the star's gravity could no longer pull it back. From that moment onward, its motion was guided only by the galaxy itself. Imagine the comet moving outward through the edge of its home system. The light of its star grows fainter. The planets become invisible behind clouds of dust. The gas that filled the inner regions thins into emptiness. The comet enters the quiet of interstellar space for the first time. It was not created for this long journey, but it carries everything it needs to survive it. The ice at its core is strong and stable. The dust that coats its surface protects it from radiation. The frozen molecules inside remain unchanged by the emptiness. Scientists believe that every star system ejects many such comets. Some are expelled early during the formation of giant planets. Others are ejected later when planetary orbits become unstable. Even our own solar system likely ejected countless icy bodies into interstellar space billions of years ago. These lost objects drift through the galaxy without ever returning. 3I Atlas is part of this wide population of wanderers. Its journey began in a moment of gravitational imbalance, far from the Sunday. Imagine the comet long after it left its home system. It had no star to orbit, no heat to shape it, no light to guide it. It drifted in darkness for ages. Stars passed slowly at great distances. Clouds of dust drifted through the galaxy. The comet remained frozen and unchanged. It could have continued like this forever. Only chance allowed it to approach the Sunday. As it drifted through the galaxy, its path slowly crossed the region the solar system occupies. It moved near the sun in a quiet glide, and for a short time its frozen interior was awakened. This long ejection process helps scientists understand the history of planetary systems. When comets like 3I Atlas appear near other stars, they reveal that ejection is common. It means that planets move and interact. It means that young systems are chaotic. It means that the dusty disks around stars produce far more bodies than the systems eventually keep. These icy wanderers are the leftovers of planet formation scattered across the galaxy like seeds in wind. Imagine the distant world that once held 3I Atlas. The star still shines somewhere in the galaxy. Its planets still orbit it. The comet's former home continues its evolution, unaware of the traveler it once cast out. Light from that star takes years to reach the place where the comet now drifts. The distance between them has become enormous. Yet inside the comet's core, the chemistry of that old world still exists. It is preserved as it was on the day it left. In the next chapter, we will explore how the sun shapes every interstellar visitor that enters its region, and how the solar system itself responds to these ancient travelers. For now, imagine the quiet moment when the comet gained enough speed to escape its home star. Imagine the first step it took into endless night and the long, silent journey that followed. When the sun first sensed the visitor, imagine the sun drifting in the quiet of space, unaware of the distant traveler moving slowly toward it. 3I Atlas had been drifting alone for millions of years. Nothing guided it, nothing disturbed it. It moved through the darkness with no destination. Then, the faint pull of the sun reached across space and touched the comet for the first time. That pull was weak at first, but it grew stronger as the comet drew closer. The sun did not know the comet, but its gravity welcomed the visitor without intention and began to shape its path. At great distances, the comet looked like nothing more than a speck of dark ice. It did not glow. It did not release gas. It simply drifted forward. The sun's influence began slowly. The comet's speed increased a little. Its trajectory bent slightly inward. For the first time in ages, the comet felt the warmth of a star, even if that warmth was still incredibly faint. This soft beginning marked the start of its brief encounter with the solar system. Imagine the comet entering the outer region, dominated by the sun's magnetic field. The solar wind flows outward in all directions from the Sunday. It fills a vast bubble known as the heliosphere. This region is large beyond imagination. The comet crossed the outer edges of this bubble long before anyone on Earth noticed it. As it crossed this boundary, the surrounding space changed. The density of interstellar particles faded. The influence of the solar wind replaced it. The comet began to feel the environment of the solar system. Nothing dramatic happened at this boundary. No flash of light, no sign of entry. The transition was gentle, yet this subtle change began to shape the comet's surface. Charged particles from the sun collided with the outer layers of the nucleus. Tiny molecules on the surface shifted. Thin layers of frost reorganized under the new environment. These small changes marked the comet's first steps into the sun's domain. As the comet moved inward, gravity slowly pulled it faster. Its long, silent drift began to accelerate. The sun remained only a bright star ahead, but the comet's speed increased with every passing day. Still, no gas escaped from its surface. The temperature remained too low for sublimation. The comet continued as a dark and quiet traveler, sliding deeper toward the sun with growing momentum. Imagine observing the comet from far above the solar system. It enters like a grain of dust falling toward a flame. The sun shines in the center, unmoving and constant. The planets circle it in their steady orbits. The comet approaches from a direction that no planet travels. It does not belong to the solar family. Its path is steep and strange. It enters from outside the familiar plane of planetary orbits. This unusual angle is one of the signs that tell astronomers the object did not originate here. As the comet comes closer, the sun begins to warm it. The first signs of activity appear. A thin and faint coma forms around the nucleus. Molecules of carbon monoxide begin to rise from the surface. These molecules escape easily at low temperatures and act as the first whisper of activity. The coma grows slowly, but remains small. The comet is still faint and difficult to see from Earth. Yet this early stage is a sign that the sun's light has reached it. Scientists watching the sky do not yet know the comet exists. It is too far and too dim. The sun is shaping it quietly without witness. The outer layers soften. A few dust grains detach and drift into space. Nothing dramatic, just the slow awakening of an object that has been frozen longer than humans have walked the Earth. Imagine the comet feeling the warmth increase as it descends. Every million miles, the sunlight becomes stronger. The coma grows slightly larger. The comet brightens by a small amount. Observers on Earth will soon detect it. But at this moment, the comet is still alone with the Sunday. It is entering a system it has never seen. It is approaching a star it will visit only once. Its long journey is reaching a moment of awakening. As the sun senses the comet's presence, the solar wind begins to shape the spreading gas. A faint tail starts to form. It is small and barely visible, but it points directly away from the Sunday. Even before the comet becomes bright to observers, the physics of the solar system begins to sculpt it. The sun becomes an artist working in gas and dust. Imagine the moment when the comet finally becomes visible to telescopes on Earth. A small streak appears in the dark of the sky. It looks like any ordinary comet, but the path is unusual. Scientists begin to follow it. They calculate its orbit. They realize it is not bound to the Sunday. This is the moment humans discover they are witnessing a traveler from another star. The sun had sensed the comet long before humans did. It had already begun its work on the ices. It had already warmed the nucleus. It had already shaped the early coma. But now the journey becomes shared. The sun warms it. Earth observes it. For a small window of time, the comet becomes part of the living story of the solar system. In the next chapter, we will follow the brightening of 3I Atlas and the scientific excitement that grew as astronauts realized the nature of this interstellar visitor. For now, imagine the comet drifting inward toward the sun for the first time, feeling the faint touch of warmth after millions of years in the cold. The first glimmer, seen from Earth. Imagine Earth turning quietly beneath the night sky as telescopes scan the darkness. Most of the sky looks empty to the human eye. Yet in that darkness, countless objects drift unseen. 3I Atlas was one of them, until the moment it became just bright enough for instruments to notice. The comet had already entered the solar system. It had already begun to awaken under the sun's faint warmth. But it was still nothing more than a dim grain of frozen material moving through the void. Then one night its light reached Earth with enough clarity for a telescope to catch it. The first detection was faint. The comet appeared as a soft point of light, with a shape that did not match any known asteroid. It showed a subtle glow around its core. That glow was the early coma forming as sunlight released carbon monoxide from the surface. Astronomers noted the unusual motion. It was moving too fast for a normal comet. Its path did not curve like the orbits of objects bound to the sunday. Even from the beginning, its trajectory hinted that it came from beyond. Imagine an astronomer looking at the data in quiet wonder. The object does not behave like a member of the solar family. Its orbit is open. Its path is steep. Its speed is high. As more observations come in, the picture becomes clearer. This is a hyperbolic object. That shape alone tells a story. It means the object is not simply passing through an elongated orbit. It is on a path that will never return. It is an interstellar visitor. As days pass and the comet approaches the sun, the coma grows brighter. The faint dust tail becomes visible. The nucleus remains too small and dark to see directly, but the gas cloud around it enlarges as more molecules escape. The early gases reveal the first clues about its chemistry. Carbon monoxide dominates the release. This is typical of extremely cold bodies. It shows that the comet has been frozen at temperatures near the deep interstellar environment for a very long time. Imagine the excitement growing among scientists. They remember the earlier interstellar objects that passed through the solar system. One was an asteroid-like shape that showed no coma. Another was a comet with unusual activity. Each visitor carried hints of the processes happening in distant star systems. Now 3I Atlas becomes part of this rare group. Its faint glow begins to speak. Its chemical releases begin to reveal the environment where it formed. As the comet brightens slightly, it becomes easier to measure. Observatories across the world point their instruments toward it. They gather spectra. They track its speed. They refine its orbit. The data begins to build a picture of a body that does not belong here. Its hyperbolic excess velocity confirms that it came from outside the sun's gravity well. Its incoming direction suggests that it wandered through the galaxy before passing near the solar system. Every measurement reinforces the idea that this is a visitor from beyond. Imagine the comet still faint, but awakening more with each passing day. The coma expands. Water begins to sublimate slightly as the temperature rises. The chemical fingerprint becomes more complex. The presence of carbon dioxide adds another layer to the puzzle. The comet's behavior becomes different from most local comets. The proportions between gases drift away from the patterns familiar to astronomers. These differences strengthen the conclusion that the object formed in a different kind of planetary environment. From Earth, the comet remains a quiet presence. It never becomes bright like the great comets of history. It does not produce sweeping tails that fill the sky. Instead, its appearance is subtle and delicate. It is a faint shimmer in the night, slowly growing as it approaches the sunday. Yet this faint shimmer holds enormous significance. It is a glimpse into a world that no longer exists. It is evidence that other stars produce icy bodies much like the ones in our solar system. Imagine standing beneath the night sky as telescopes track the comet's progress. The object is too faint to see with the naked eye, but the knowledge of its presence fills the darkness with a sense of wonder. Somewhere beyond the atmosphere, an interstellar traveler is awakening under the Sunday. Its slow brightening tells a story that began billions of years ago around a distant star. As astronomers gather more data, the comet becomes one of the most studied faint objects in the sky. Its composition, its gas release pattern, its motion, all of these details reveal parts of its past. The calm brightness curve shows no sudden outbursts. The comet behaves steadily. This stability is unusual for a body experiencing the sun for the first time. It suggests a strong nucleus, a compact structure, a balanced distribution of ice and dust. In the next chapter, follow the growing scientific focus on the comet as it moved closer to the sun, and the moment when its interstellar identity was confirmed without doubt. For now, imagine the faint first glimmer of the comet seen from Earth and the quiet excitement it brought to those who recognized what it truly was. The moment its interstellar nature became certain. Imagine the comet drifting steadily inward, while astronomers around the world continue measuring its motion with growing precision. Each observation adds another point on a long, invisible curve. The curve represents the comet's path through space. At first, there is uncertainty. Its orbit could be long, it could be strange, it could be highly elongated yet still part of the solar system. But as more measurements come in, the truth becomes clear. The curve does not close. It remains open. It does not bend back toward the Sunday. Instead, it stretches outward toward infinity. This is the hallmark of an interstellar visitor. For the astronomers who follow the object, this realization unfolds slowly but unmistakably. They calculate the comet's incoming speed. It is slightly higher than the escape velocity of the Sunday. This means that no matter how close it comes, no matter how warm it becomes, it will never be captured. It will never revolve around the sun again. Its orbit is hyperbolic, and this shape reveals the story of its origin. A comet born in the solar system could not achieve such a path without a dramatic gravitational push. But nothing in the solar system provided such a force. The comet's speed and direction show that it arrived already unbound. Imagine receiving this information at a quiet observatory late at night. A faint speck that seemed barely noticeable is now revealed as a visitor from another star. The night sky feels different. The familiar constellations seem to expand. The idea that something drifted across the galaxy for millions of years only to pass near Earth adds a sense of vastness to the moment. It deepens the awareness that the galaxy is not distant. It is all around us. And now part of it has come close enough to study. As the comet glows softly under increasing sunlight, the chemical signatures become clearer. The presence of carbon monoxide at high levels reinforces the idea of a body that formed in extreme cold. Local comets show one pattern. Interstellar ones show another. This comet's chemistry leans toward the interstellar pattern. Its behavior matches its orbit. Everything about it aligns with the idea that it never belonged to the Sunday. The comet becomes a bridge between one star and another. Imagine scientists analyzing the spectra. Each line tells them something about the comet's internal structure. The ratios of gases hint at temperatures far lower than the early solar system. The dust grains within it have specific mineral signatures that differ from the usual mix expected in our own comet population. These minerals carry the fingerprints of the star that once gave the comet its raw materials. They reflect the environment of its birth. They mark it as a child of another sun. By now, telescopes across Earth and in orbit follow the object regularly. Its brightness profile is steady. It does not break apart violently. It does not behave like the fragile visitors that sometimes crumble under solar heating. Instead, it remains stable. This stability supports the idea of a compact nucleus. Perhaps its interior was shaped by slow compression early in its formation. Perhaps its materials clung together more tightly than those of typical comets in the solar system. The differences grow clearer with every observation. Imagine the comet deepening its approach as the sun warms it further. Dust and gas stream away. The coma expands. Each observation increases the certainty about its identity. The scientific community begins to share the news. It has become the next known interstellar comet, one more wandering body, joining the small group of visitors from outside the solar system. A rare opportunity stands before everyone. For a short time, the comet will reveal secrets about a star system that may be long gone or changed beyond recognition. The scientific excitement is gentle but steady. There are no dramatic flashes, no bursts of brightness that capture the public eye. Instead, the comet provides a quiet, continuous release of information. It allows scientists to study interstellar chemistry in motion. It allows them to compare two different planetary nurseries. It becomes an interstellar textbook written in ice. Imagine an astronomer standing under the night sky knowing the comet is there, though too faint to see. The sky feels more connected, more alive. The comet is not a distant abstraction. It is a real object moving through the same cosmic neighborhood as Earth. Its presence is subtle but profound. It is a reminder that the galaxy is not empty between stars. It is filled with travelers and remnants of distant worlds. As the comet moves closer to the sun, the confirmation of its interstellar nature becomes absolute. Its orbit settles into a precise, hyperbolic shape. Its velocity remains above the solar escape speed. Its chemical identity remains unusual. Every piece aligns. The comet is an interstellar visitor, a traveler from a birthplace humans will never see. In the next chapter, we will follow the comet as it approaches perihelion, and how astronomers prepared to watch its closest moment with the Sunday. For now, imagine the soft realization spreading through the scientific community that this quiet, faint object is a messenger from another star, carrying ancient memories through the solar system before drifting onward into the dark, preparing for its passing. Imagine astronomers around the world watching the slowly brightening glow of the comet as it moved deeper into the solar system. They knew its time near the sun would be short. They knew its closest approach would be its only chance to reveal its deepest secrets. For millions of years it drifted in darkness, and now it would awaken for only a moment. Every observation mattered. Every instrument needed to be ready. As the comet approached perihelion, the sun's warmth increased. Spectra showed rising levels of carbon monoxide, water vapor, and other gases. The coma grew with slow, steady grace. No violent bursts. No unpredictable outflows. The comet behaved calmly, as if it had been shaped for this moment over countless ages. This stability allowed astronomers to build detailed plans. They knew how bright it would become. They knew when its gas release would peak. They prepared their telescopes for the moment of closest approach. Imagine teams adjusting instruments across continents. Observatories booked long sessions. Space-based platforms aimed their detectors toward the predicted coordinates. The comet was faint but rare. It was a visitor from outside the solar system. There would be no second chance. Once it passed the sun, it would disappear into darkness forever. Scientists scheduled radio telescopes to capture molecules invisible to optical instruments. They arranged to collect infrared data that would show heat rising through the dust. The comet drifted onward, unaware of the attention. Its coma thickened. Its tail formed a delicate ribbon behind it. Dust grains lifted easily in the strengthening light. The nucleus stayed strong and unbroken. Many comets fragment before or during perihelion, but this interstellar traveler held together. Its structure seemed unusually compact. The way it released gas suggested layers of ice arranged in a stable pattern, formed under the extreme cold of another star's distant nursery. Imagine the final week before perihelion. The comet moved through a region of increasing sunlight. The activity grew a little faster. Molecules trapped deep inside began to rise. Some of these ices had not been warmed since the comet left its original star. They carried chemistry untouched by time. Astronomers watched carefully as these signatures entered the coma. They hoped to find clues about the material that existed in that distant system when the comet formed. The orbit became incredibly precise now. Calculations confirmed its interstellar nature beyond all doubt. Its speed remained higher than a solar-bound comet could achieve. Its incoming direction did not match any local family. Its exit path was set. It would leave the solar system forever. Telescopes aimed themselves for the moment when its distance from the sun would be at its smallest. Imagine sunrise over observatories preparing for the event. Operators aligned, mirrors calibrated sensors, and checked timing again and again. The comet approached the sun with immense speed. Soon the light would overwhelm its nucleus. Soon the coma would glow brighter than at any point in its journey. The window would be brief. Instruments had to be ready before the comet entered the glare. They would capture the moment or lose it forever. In these final hours before perihelion, the comet moved steadily and without hesitation. No outbursts disrupted it. No sudden changes marked its path. It drifted, as it always had, following the line gravity created long ago in a different part of the galaxy. Its moment near the sun was near. The world watched and waited. In the next chapter, we will follow the comet through its closest point and the quiet fire that shaped its brief moment of greatest activity. For now, imagine the calm before the brightest moment of its long, ancient journey. The quiet fire of perihelion. Imagine the comet reaching the final stretch of its long inward journey. For millions of years it drifted through cold, silent space. For months it moved toward the sun with increasing warmth. Now the moment of perihelion arrives. This is the closest point to the Sunday, the point where light and heat embrace the comet more strongly than at any other time. The point where its ancient ices feel temperatures they have not experienced since the comet was born. As the comet swings inward, its speed becomes enormous. Gravity pulls it rapidly along its path. The sun fills more of its sky. Radiation becomes intense. Dust rises from its surface in slow, delicate streams. What appears gentle on a cosmic scale is actually powerful. Molecules long trapped in the ice are released. They rise into the coma and drift outward to form the glowing cloud around the nucleus. Imagine the nucleus responding like a frozen seed touched by warm breath. Surface layers crack. Pockets of ancient gas escape through thin vents. The coma thickens. It reflects sunlight in a soft haze that surrounds the dark core. There is no explosion, no violent burst. Instead, the awakening is smooth. The comet behaves with quiet balance. Many comets fragment under such heat, but this one remains stable. It keeps its shape. As it passes through perihelion, the chemistry of the coma shifts. New gases appear. Molecules that require greater warmth emerge from deeper layers. These molecules carry information about the comet's birthplace. They reveal conditions far colder than the early solar system. They hint at a star surrounded by a disk with different gradients of temperature and dust. The comet becomes a messenger. It reveals fragments of a world that may no longer exist. Imagine astronomers watching the data in real time. Lines in the spectrum change. They widen. They strengthen. They reveal patterns unseen before. The comet is speaking in the language of chemistry. It releases memories frozen since its formation. Every molecule tells a story. Some describe ices shaped in darkness. Some point to dust grains formed beside another star. Others suggest minerals rare in the solar system. The coma grows at a steady pace. No eruptions disturb it. The tail points away from the sun in a thin, elegant line. Sunlight pushes dust outward. Gas flows freely into space. The tail stretches like a thread across the solar wind. Imagine the comet passing closest to the Sunday light floods its surface. It glows faintly in the brilliance. The nucleus rotates slowly. Each region receives its brief moment of heat. Ices evaporate. Dust rises into the expanding coma. Still, the comet holds together. This stability allows astronomers to observe clearly. It becomes a rare moment where interstellar ice meets the intense radiation of the Sunday. As perihelion peaks, the comet reaches temperatures unimaginable during its long time in interstellar space. The warmth is brief, but powerful. Soon, it will cool. Soon the deep layers will lock themselves again in silence. The gases that escape now carry with them the oldest memories of the comet. They carry the signature of the star where it formed. Imagine the comet now drifting outward. The moment of maximum brightness fades. The coma will begin to shrink. The tail will thin. Sublimation will slow. But for this brief moment, the comet shone as brightly as it ever would. It experienced the height of its encounter with the Sunday. Astronomers continue gathering data. They study gas release rates. They study dust grain properties. They compare the comet's behavior to other interstellar objects. Each detail expands the understanding of how icy bodies from other stars respond to solar heating. Imagine watching the comet from space. The sun burns at the center. Light fills the inner system. The comet curves through this brightness like a quiet visitor moving through a silent cathedral of light. It leaves perihelion behind. The encounter fades. The journey continues. In the next chapter, we will follow the comet as it cools and begins its long retreat into the dark. For now, imagine the peak warmth melting away while the comet glides outward with ancient calm. The slow cooling after the sun. Imagine the comet passing beyond its closest point to the Sunday. The moment of greatest heat is behind it. Light begins to soften. The radiation that once pushed at its surface grows weaker. The comet continues forward, carried by the immense velocity it gained on its inward path. Its distance from the sun grows. With each passing hour, the warmth fades. As the sunlight weakens, the release of gas slows. Molecules that escaped easily during perihelion now retreat into silence. The coma becomes thinner. The cloud around the nucleus softens into a faint sphere. Dust continues to drift outward, but at a lower rate. The comet begins to shed less material. Its surface shifts back toward the cold state it held for ages before coming near the Sunday. Imagine the nucleus settling as though exhaling. Cracks created during the heat stiffen. Outer layers lose energy and return to stillness. Deeper pockets of gas that once rose now lie dormant. The warm phase ends. The comet grows quiet again. It returns to the condition that defined most of its life. For astronomers watching the comet, the change appears in graphs and images. The brightness curve drops gently. The tail contracts. The coma shrinks. Activity falls into steady decline. Spectra show fewer molecules. The comet's voice softens as it moves into cooler space. Imagine the comet drifting outward. The sun grows smaller behind it. The solar wind loses strength. The long ribbon of dust behind it stretches thinner until it dissolves. The comet returns to its original form. A dark, icy body drifting alone. The brief flare of activity near the sun becomes only a memory pressed into its altered outer layers. The comet and the sun part ways. The warmth no longer reaches it. The nucleus freezes once more. Activity falls to almost nothing. Only the most volatile ices release small amounts of gas now. Soon even that will stop. Imagine the scientists gathering the last data. They study how the comet behaved before and after perihelion. They examine the tail. They analyze the fading gas. Their work deepens the understanding of interstellar objects. Observations like this are rare. They hold enormous value. As the cooling continues, the comet becomes almost invisible. Even powerful telescopes struggle to detect it. Its coma fades into darkness. The nucleus hides again in shadow. The object becomes what it always was. A silent wanderer shaped by the cold. Imagine watching the comet shrink into the distance. First a dim point, then nothing. The sun's influence slips away entirely. The comet cools into silence. It prepares for its next phase. The long outward journey into the deeper parts of the heliosphere. In the next chapter, we will follow the comet as it moves toward the outer boundary of the solar system. For now, imagine its fading glow drifting into the dark, quiet regions beyond the sun's warmth. Leaving the solar system behind, imagine the comet drifting farther from the sun as the days pass. The warmth that once stirred its surface has faded. The solar wind grows weaker. The bright region of the inner system lies behind it now. Ahead is the long, quiet path toward the outer reaches of the heliosphere. The comet continues at high speed, but everything around it becomes calmer. Light softens. Heat disappears. The deep cold returns. As the comet moves outward, the coma becomes too faint to see. Only the densest grains of dust remain near the nucleus. All other particles spread into the vastness. The tail that once pointed away from the sun stretches thinner until it dissolves. The comet returns to its oldest form, a small, dark body drifting through space. Imagine the solar system from above. The planets circle the sun in quiet loops. Their orbits form a wide, flat disk around the star. But the comet does not follow this plane. Its path rises away from it. It arrived from an unusual direction, and now it leaves along another. This strange angle is the signature of an interstellar traveler. Far from the sun, the temperature around the comet drops sharply. Any remaining activity ends. The nucleus becomes completely dormant. It feels the deep cold that defined most of its existence. The outer layers freeze hard. Cracks stiffen. The last trace of heat escapes. The comet becomes stable and still. Imagine the outer solar system waiting in silence. Here, the sun is just another bright star. Dust is thin. Ancient icy fragments drift unnoticed. Some belong to the Sunday. Others may be visitors like the comet. The region is calm. Objects pass one another with vast distances between them. The comet moves through this silence with ease. Its speed is too great for the sun to hold it. Gravity weakens. The comet approaches the heliopause, where the solar wind meets the pressure of the galaxy. It crosses this boundary without noticing. There is no change that the comet can feel, but the environment shifts. The dust of the solar system fades. The particles of interstellar space appear again. Astronomers watch the faint speck until it becomes too dim to track. They record the final measurements. They save the last images. They know the comet will never return. It now follows the same freedom it had before entering the solar system, a path set by the gravity of the galaxy. Imagine the sun behind the comet now. It grows dimmer. It no longer warms the surface. It becomes one point of light among billions. The encounter ends. The comet moves outward into the vast openness of the Milky Way. For years and centuries, the comet will continue without interruption. It will cross regions empty of dust. It will pass near distant stars without approaching close enough to warm. It will remain frozen, unchanged, and eternal. In the next chapter, we follow the comet as it returns fully to interstellar space. For now, imagine the solar system shrinking into a faint glow behind it, while the galaxy opens before it like a dark and endless sea. A wanderer returning to the stars. Imagine the comet now leaving the solar system entirely. The sun has faded into a distant point. The warmth that once stirred its surface is gone. The comet drifts into interstellar space. The great quiet surrounds it again. This is the realm it knows best. A place without orbits or seasons. Only emptiness and the faint glow of stars. As the comet continues outward, the last traces of the solar wind fall behind. Ahead lies the interstellar medium, a vast ocean of thin gas and drifting dust. Cosmic rays pass through in silence. Tiny grains float like forgotten shadows. The comet moves through this space, carried by the momentum it gained near the Sunday. Imagine the nucleus rotating slowly. One side faces faint starlight, then the other. No warmth rises. No gas escapes. The nucleus is silent. Frozen molecules lie still. The surface remembers the sun in small patterns created by sublimation. But these marks fade as the cold deepens. The comet returns to the form it held for most of its existence. Far ahead, the galaxy stretches in wide spirals. Star clusters drift like islands. Clouds of gas glow softly. New suns are forming. Old suns are dying. The comet will pass through these regions over millions of years. Perhaps it will one day come close to another star. Perhaps that star will warm it. Perhaps it will awaken again. Or perhaps it will drift forever untouched. Imagine the distant star where the comet began. It may still shine. Its planets may still circle it. Or it may have changed. Stars evolve slowly. Worlds shift. The comet left that place long ago. It carries only the chemistry of its birth. It remembers a time when dust and gas circled that ancient star in a wide disk. The comet may pass near stars as it travels. Gravity may bend its path. A tiny shift one century, another shift the next. Over long stretches of time, these changes may guide it toward a new system. Or they may carry it through open space without interruption. The comet does not choose. It follows gravity alone. Imagine the galaxy living its slow rhythm. Stars orbit the center. Gas clouds collapse into new suns. Supernovae scatter elements through the Milky Way. Through all this motion, the comet remains quiet. It is older than many stars. It will outlast many more. It is a witness to celestial history. As the comet moves deeper into interstellar space, its visit to the sun becomes only a brief chapter, a moment of light in an otherwise dark existence. The warmth touched only the surface. The deeper layers remain unchanged. The ancient chemistry remains preserved. Imagine the vastness ahead. The comet continues without slowing. The sun becomes a faint star behind it. The galaxy opens before it. The comet belongs to this expanse. It always has. Its time with the sun is over. Its journey continues. Quiet, endless, eternal.